Alright, you've done the gizmo where you played with the temperature, the concentration, particle size, or surface area, and catalyst. So we're going to talk about what happens. When you increase the temperature, then you should have had an increase of your rate. If you lower the temperature, then the rate at which the reaction occurred should have decreased. And also at this point you've already, or should, depending on when you're listening to this, have done the activity where you're going to do hands-on on all of this. Higher concentration, you have more collisions. Sorry, I'm working with a new thing today. So the more collisions you have, the faster it's going to go. And so obviously lower concentration is going to be the opposite of that. Particle size or your surface area. The more surface area you have, meaning the smaller particle size, the faster it's going to go. So you're going to have an increase in the rate. And minimum surface area means you're going to have bigger pieces. It's going to be lower. A catalyst helps a reaction. It speeds it up by changing its energy of activation. We'll talk about that in just 1 second. And so it helps lower your energy of the energy of activation, meaning it'll make it go faster. And an inhibitor does the opposite thing. It stops or slows down a reaction. A common way of inhibitors, some of you may know, when you cut up apples, if you put lemon juice on the cut up apples, if you were taking them to school, whatever, that would help the apples keep from browning. So that's an inhibitor. It makes it happen slower than it would normally do. Okay, energy reaction diagrams. You always start with your reactants. So your reactants are here, and your products is what you end up with. It's always a left to right process on these. Every reaction has to overcome the hump of energy required in order to occur. So the energy of activation is where your energy level is for the reactant, how far up it has to go in order for those reactants to start converting into your products, and then it goes down. So you can see that the energy of activation with the catalyst is lower, so it's got a lower hump to overcome for your products. Your activated complex is at top. That is from the gizmo when the two little molecules came together. That was your activated complex. Sorry, writing. That was your activated complex when they came together before that, while they're shaking, and then when they separated, that's when they started the downward flow to the products. An inhibitor would be have the opposite reaction of a catalyst, so it would end up being a higher level of energy required for that reaction curve. That activated complex is at the top of each of the humps. Okay, rate laws. This is the general formula where you have the amount of time it takes is equal to a rate constant, a specific temperature and everything else, times the concentration of one reactant to a power that has to be determined through experimentation and math, times the next reactant that's through experimentation and math, and so on and so forth. How you can have more than two. You can have just one reactant breaking down. It's going to have a rate law and everything else. So I'm going to talk about how to make those calculations, because that's what we're going to be doing in class on Monday. So K is your constant. X and Y are the orders of the reactants, and I'll talk about, and that means how does one reactant cause a bit more of a change than the other reactant. The overall order is once you find your rate law, you just add your superscripts together, and we're going to do that together. We're going to calculate a rate law. We're going to do the overall, and we're also going to calculate K. And the superscripts are sometimes they're the same as their coefficients, but not always. So don't think that you can just look at a reaction and figure out what the rate law is based on the balanced chemical equation. All right. So the example we're going to do is we're going to find out the reaction between bromate and bromide ions in acidic aqueous solution is given by the equation below. That's just telling me this reaction occurs. 4 experiments were performed. You have to do multiple experiments, and in these experiments the only thing that you're changing is your concentrations to find out the effect of different concentrations to see how the concentration of one reactant controls the reaction more than another one. So make sure you copy down these the charts so that you know where I'm getting everything from. So we're going to find the rate law, we're going to find the order, and we're going to find K. So your general formula is your rate equals your K times the BrO3 minus, you plugging in where your A and your B was with the different reactants. That's what I did right there. So we're going to solve that. The rate law is when we have our superscripts figured out. So to find my X, I find 2 experiments where the BrO3 is changing, but the Br and the H is not changing, because when you're doing the math, you want to be able to cancel out stuff. Those are the same, and those are the same. Your K's are the same. So everything else is not the same, so you have to do some math. And you find that your 2 different rates, experiment 2 over experiment 1, is equal to 2-ish. And then 0.2 divided by 0.1 is 2, and it's raised to the x. Well, 2 equals 2 to the x. That means that x must be 1. So we do the same thing. We find another reaction where the BrO3 and H plus are the same between the individual reactants, and where the Br minus is the only thing changing. Of course, your K's are canceling out still. Let me change. So your K's are canceling out. Your 0.2 to the first and your 0.2 to the first are canceling out. Your 0.1 to the Z and 0.1 to the Z. So when we divide our numerators by our denominators, we get 2 equals 2y. So y equals 1. Final thing is to find Z. And you can see at the top I keep putting in the numbers that we know. So to find Z, I chose experiments 4 and 1. At this point, once you know all of your different numbers, you should be able to use any 2 experiments to figure that out. And I just realized I had a mistake. I didn't change these out. That's a 1, and that's a 1. We already figured those out. So again, our K cancels out. The 0.1 to the first and the 0.1 to the first cancels out. The 0.1 to the first and the 0.1 to the first cancel out. So we do the math related to the numbers left. So you get 4 equals 2 to the Z. So Z has to be 2, because 2 squared equals 4. And whenever possible, I always make sure I can cancel everything out just to make the math a lot easier. So to finish up, we see that we plug in our x, y, and z here. So our rate law, when we're determining it, and then you have to actually write it out, is your rate is equal to your K times the concentration of your BrO3 minus to the first, times your Br minus to the first, and times your H plus to the second. Your overall order is 1 plus 1 plus 2 equals 4. And if we're asking, if I said, what's the order for BrO3? It's a 1. The Br is a 1, and then the H plus is a 2. So those are their individual orders, meaning how does the changing of those concentrations affect the rate. And then for overall, for the whole reaction, that's where you add them together. If we want to determine K, we can pick any experiment. It does not matter of the 4, just any one of the 2 of them. And you can check me out on this. Plug in 8.4 for all of the other numbers, and you'll find that you're getting close to the rates with some roundings going on. So I took experiment number 1. Its rate was 8.4 times 10 to the negative 4 equals K, which is my unknown, times 0.1 to the first, times 0.1 to the first, times 0.1 to the squared. I rearranged to isolate my K. I plugged in the calculator and found out that the K value is 8.4.